Have you ever just, stared at some complex software, maybe an online checkout, or even just something running in the background, and wondered how all the pieces actually talk to each other?
Yeah, what's really going on under the hood? Not the code lines, but
Yeah.
the actual back and forth.
Exactly, like the choreography, the conversation,
Yeah.
that sequence of requests and replies happening in a really specific order.
Trying to figure that out just by reading docs or logs, it's usually pretty painful. You really need a map, a visual one.
Right. And that map, that blueprint that, well, frankly, architects and developers rely on is the UML sequence diagram.
Hmm.
So today we're doing a deep dive. We've looked at the tech docs, the tutorial, the real world examples, our mission to give you a shortcut.
We want you to go from maybe just seeing these diagrams
Yeah.
to actually reading them, understanding them pretty quickly.
Yeah, understanding not just the symbols, but the why, how they reveal potential problems like bottlenecks or just how different parts of a big system are divided up.
It's about grasping that architectural story they tell.
Okay, let's unpack this. So at its core, what is a sequence diagram really showing us?
It's all about how different parts of a system, objects, classes, components, interact over time. The big focus is the sequence. What happens, then what happens next.
And why this specific diagram? Why is it so, well, essential?
I think it's the dynamic view. Other diagrams might show you the static structure, like who knows about whom.
Right, like a class diagram.
Exactly. But the sequence diagram shows the behavior, how things actually work together when the system is running. Super important for things like microservices.
Yeah, because one action might trigger calls across several different services.
Precisely. And trying to trace that without a visual guide is, well, it gets complicated fast. This turns that abstract flow into something you can actually follow.
So it's not just describing something that exists, it helps you design it too.
Definitely. The sources really emphasize its role in design, especially when you're figuring out a use case. Step by step, how does the system need to respond to achieve this user's goal?
And for fixing things when they break.
Oh, absolutely crucial for troubleshooting. If you have a diagram showing the expected message flow for, say, a successful login,
Hmm.
and something goes wrong, you can pinpoint exactly where that flow breaks down. Where did the message not get sent, or where did the wrong reply come back?
Okay, so to start reading one, we need to know who the players are. The sources talk about two main types of participants. First up, actors.
Right, actors. Those are the stick figures you usually see on the left. They're external to the system you're modeling.
Like a person using an ATM.
Perfect example. Or it
Well,
could be another system, maybe an external payment service. They kick off the interaction, but they're outside the boundary of what you're diagramming internally.
Okay, so actors are outside, then you have the things inside the system.
Those are the objects or instances, represented by the rectangles across the top. These are the actual components doing the work.
So like the login service, the user database, the shopping cart object.
Exactly.
Yeah.
The pieces of your software you're interested in modeling the interaction between.
And running down from each actor and object is that dashed line, the lifeline.
Yep, the lifeline. It just represents that participant's existence during the scenario you're modeling. As you move down the lifeline, time progresses.
Simple enough. Actor, object, lifeline, showing time passing.
That's the basic stage setup.
Okay, here's where it gets really interesting then. How these components actually talk to each other. The messages.
Right, the messages are the core. They're the arrows going between the lifelines, showing communication happening. And they appear one after another, moving down the diagram, showing that sequence in time.
And the type of arrow matters. A lot, it seems.
Oh, absolutely. The arrowhead style tells you about the nature of the communication. Let's hit the main three. First, the synchronous message.
Okay.
Solid line, solid arrowhead. Think of a standard function call. The crucial thing here is the sender waits. It sends the message and then just stops, waiting for a response before it does anything else.
Makes sense for code running all in one place. But if that message is going across a network, like my web browser waiting for a server halfway across the world.
Exactly. That synchronous waiting can introduce serious delays, latency. If the Login UI makes a synchronous call to an auth controller, which then makes another synchronous call to a database, those waits add up.
So how do we show a message where the sender doesn't wait? Like it just sends it off and moves on.
That's the asynchronous message. Solid line, but with an open or lined arrowhead. It's like fire and forget. The sender dispatches the message and immediately continues its own work. It doesn't block. This is, well, pretty fundamental for building responsive systems, especially distributed ones. You delegate a task without halting your own progress.
Got it. So synchronous waits, asynchronous doesn't. What about the answer coming back?
That's typically the reply or return message.
Hmm?
Dash line, usually with an open arrowhead, going back from the receiver to the original sender.
That's what signals the end of the wait for a synchronous message.
Exactly. It delivers the result, or just confirms completion, and lets the original sender continue. Understanding synchronous versus asynchronous, that's probably the most critical distinction here. It has huge implications for performance and system design.
Yeah, I can see that. Okay, so we know who's talking and whether they wait or not, but how do we see when an object is actually busy doing something versus just waiting?
Good question. That's the job of the activation box, also sometimes called the focus of control.
That thin rectangle that appears on the lifeline.
That's the one. It's drawn right on the lifeline, and its length shows the duration that the object is active processing a message, doing calculations, whatever.
So a really long activation box might indicate.
It might indicate that object is doing a lot of work, or potentially it's a bottleneck. If it's active for a long time, especially if others are waiting on it via synchronous calls, that's a place you'd look for performance issues.
It gives you a quick visual clue about processing time. Actors don't get these right because they're external.
Generally, no. The focus is on the internal system components and when they are active.
Okay, that makes sense. Now, real systems aren't just straight lines of messages. There's logic, right? If this, then that, or do this thing multiple times.
Exactly. Simple sequences are fine, but you need ways to model conditions and loops. If you just drew all possible paths linearly, the diagram would become an unreadable mess very quickly.
So how do we handle that complexity?
Using combined fragments, these are basically boxes drawn around sections of the sequence diagram, labeled with an operator that tells you the type of logic inside.
Like control flow structures in programming.
Very similar concept, yeah. They manage the complexity and show the decision points. The most common one you'll see is probably the alternative fragment, labeled alt.
The if-then-else.
Pretty much. It shows two or more mutually exclusive options. The fragment is divided into sections, each with a condition, called a guard. If the condition for the first section is true, you follow that sequence of messages.
And if it's false?
Then you check the condition on the next section, and so on, like an else-if or a final else. The key is only one of the sections within the alt fragment will execute for any given run.
Okay, so alt is for choices between paths. What about something that might happen or might not, like a simple if?
For that, there's the optional fragment, labeled opt. It just has one section with a condition. If the condition is true, the messages inside the opt box execute. If false, you just skip it entirely and continue with the sequence after the box.
So alt sources a choice between paths. Opt is just a maybe do this step.
You got it. And then there's the loop fragment, loop, for repetition.
Like checking inventory for each item in a shopping cart.
Exactly. The messages inside the loop fragment repeat as long as a certain condition holds true, or maybe for a set number of iterations.
These fragments seem essential for showing anything beyond a trivial flow. But I can also see how even with these, a diagram for a really complex process could get huge and hard to follow.
Absolutely. That's a major challenge. And it leads us to another really important fragment, the reference fragment, or ref.
How does that help?
Think of it like calling a function or a subroutine. The ref fragment is a box that basically says, okay, at this point, a whole other interaction happens, and the details are defined in another sequence diagram.
Ah, so you can break down a massive process into smaller, more manageable diagrams.
Precisely. Instead of cramming, say, the entire process payment logic into your main checkout diagram, you just put a ref box labeled process payment. It keeps the main diagram clean and focused.
That seems less like a last resort and more like good practice for complex systems.
It is absolutely good design practice.
Right.
It encourages modularity and helps you manage complexity. You can focus on the interactions at a specific level of abstraction without getting lost in the weeds of every single sub-process.
Keeps things readable. Okay, this is making sense. Let's try to tie it all together. The sources use a user login system example. Can we walk through that?
Sure. It's a classic example and uses several of these elements. So the participants are the user, that's our actor.
Right, the stick figure.
Then the Login UI, the interface the user interacts with. Then the auth controller handles the actual logic of checking credentials. And finally, the database.
Okay, 4 participants. How does the flow start?
It starts, naturally, with the user. They enter credentials, username and password, into the Login UI. That's likely a synchronous message.
Okay, so the Login UI's activation box starts. It's now active.
Right. The Login UI then takes those credentials and sends a login message, probably also synchronous, to the auth controller. Now the auth controller becomes active.
And the auth controller needs to check against the database, right?
Yep. So it sends a message, maybe find username, again, likely synchronous, to the database.
Now, the database lifeline gets its activation box, but probably a short one.
Usually, yeah. Databases are optimized for quick lookups. So it does its query, finds the record or doesn't, and sends back a reply message, maybe user record, to the auth controller. The database's activation box ends.
Okay, auth controller has the info it needs. Now comes the logic part.
Exactly. This is where we'd see an alt fragment, the
Okay.
big decision point.
Condition 1, success.
Right. The guard condition might be something like user exists AND password valid. If that's true, the sequence inside this part of the alt fragment runs.
Which would be?
The auth controller sends maybe a login success message back to the login UI.
Okay.
And the login UI then probably calls something like show welcome page
Mhm.
to update the display for the user. The interaction for success is complete.
Makes sense. But the other path, the failure path within the alt.
Crucial. The condition there would be the else case, or maybe explicitly, user doesn't exist or password invalid.
In the messages.
The auth controller would send a login failure message back to the login UI.
Which then shows an error to the user, like shower message.
Exactly. But here's where you might see another message type too. The auth controller, on failure, might also send an asynchronous message, say log failed attempt username, to a separate logging service object.
Ah, asynchronous, because we don't want the user to wait while we log the failure. It's a background task.
Precisely. Fire and forget. The login failure response goes back to the UI immediately, while the logging happens independently.
That's a great illustration. And looking at the whole thing, you'd probably see longer activation boxes on the login UI and auth controller compared to the database?
Typically, yes, because the UI and controller are coordinating the flow, handling logic, waiting for replies. The database just does its quick fetch or check. It visually shows where the time is spent and where the complexity lies.
Wow, okay. That example really helps solidify it.
Brings all the pieces, lifelines, messages, activations, fragments together in a practical context.
So, wrapping this up a bit, this has been a really insightful deep dive. Sequence diagrams are fundamentally about visualizing that dynamic behavior, the interactions over time.
Yeah, using the lifelines to show existence over time, the different message types, synchronous, asynchronous reply, to show communication style.
The activation boxes to show when components are busy, and those critical combined fragments like alt, opt, loop, and ref to manage logic and complexity.
That's the core vocabulary, definitely.
But you mentioned challenges. It's not always easy.
No, it's not.
Yeah.
The sources are clear on this. The biggest challenge is often just complexity.
Hmm.
Real systems have lots of interactions. If you try to show everything on one diagram,
It becomes unreadable, hence the importance of ref.
exactly. Using ref to break things down is key. Another challenge is finding the right level of abstraction. You don't want to model every single line of code, but you need enough detail to be useful.
Finding that balance.
And the final big one, keeping them up to date. Systems change, code evolves. If the diagrams aren't maintained alongside the code, they quickly become misleading or just plain wrong.
That sounds like a serious commitment. If they're hard to maintain, why bother? Isn't the code the real source of truth anyway?
The code is the ultimate truth, yes. But it's not always a truth that's easy to understand, especially for complex interactions or for people who aren't deep in that specific code base.
Ah, so the diagram is like the shared understanding.
Exactly. It's the shared language. It allows a whole team, developers, architects, even business analysts sometimes, to quickly grasp the intended flow, the architectural decisions, the dependencies. You just can't get that same high-level, quick understanding from thousands of lines of code.
It bridges that gap between the requirement and the implementation detail.
Well put. It communicates the intent of the interaction flow.
So for you listening, what does this all mean? Well, next time you're interacting with some complex service, maybe you're placing an online order, where it has to check inventory, process your payment, schedule shipping.
All those hidden steps.
Right. You now have this mental toolkit to actually visualize what might be happening behind the scenes. You can picture those lifelines, those messages flying back and forth, maybe even guess where the synchronous waits are happening.
You can start to see the blueprint, the choreography that makes that simple button click actually work, or sometimes makes it feel slow.
Yeah. Think about the last time an app or website felt sluggish. Could you mentally sketch out which activation box might have been running too long? Or was there a synchronous call holding everything up that really should have been asynchronous?
That kind of intuitive analysis, that's the real power you gain from understanding these diagrams.
Thank you for joining us for this deep dive.